Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome to Module 5. So you know, in this week, we have gone through again a lot of things, and basically it is about thermoelectricity, and we obtained an expression for these currents driven by temperature, and which was basically the same expression as we had in week 1. And we also obtained an expression for the heat current that is associated with the flow of electrons. And by linearizing those, we obtained finally the set of coefficients, these transport coefficients. The G, which is exactly what we had before in week 1, and it is obtained by doing this integral, this averaging over energy that we talked about in week 1. And there are also these three new additional transport coefficients which we have obtained. And I've kind of written them like in a row. The idea is up to here is the same no matter which coefficient you want. If you want conductance, then you should take what we have here, multiply by 1, which means basically do nothing. So that's our old expression. You can take what we have here, multiplied by that factor, and then you'll get GS. You can take what we have, multiplied by that factor, and then you'll get GP. And if you take it and multiply by that factor, you'll get GQ. So I've kind of written them all in a row so you can see them at a glance. And then the actual experimental coefficients are things like the Seebeck coefficient, which is the ratio of GS to G, or the Peltier coefficient, which is the ratio of GP to G. And as I mentioned in my last lecture, there is this basic relationship between GP and GS, which you can see from the expressions here, that GS, that there is just if you multiply GS by the temperature, you get GP. And similarly, if you multiply the Seebeck coefficient by temperature, you get the Peltier coefficient. Again, an experimentally established fact, I think known as the Kelvin relation. And then we have something that you could call the heat conductivity, that is the heat current carried by electrons due to a temperature difference. And this involves all of these coefficients, all 4 of them in a slightly complicated way. But this then would be something, but once you have these coefficients, you could evaluate it. So formally then, this would be the basic approach. This is it. We have expressions for all the currents. If we know how to calculate conductance, we know how to calculate all the rest of it. Now what I want to show you is, in this lecture, we'll apply this to a particularly simple device. You see, a device where, let's say, I just have a single level. So I've got so this is energy as before. But rather than have a continuous density of states, let's say we just have a single level at a certain energy epsilon. Just a single one. Okay? And what we'll do then is, we will calculate all these different coefficients. You see, we can do that, of course, using the formal expressions. But what I'll try to show you is, just instinctively, you can find all the right answers quite easily. See? And that's kind of instructive, doing that, and then comparing them to what you get formally. Okay? So the picture we have then is, we've got these 2 reservoirs, mu1 and one with mu1 chemical potential and a temperature of T1, and the other has mu2 T2. And you've just got one level. Okay? So now the first question is, what is the Seebeck coefficient? Now, what is a Seebeck coefficient then? Well, experimentally, what it means is, we are asking, what is the voltage for a given temperature difference if the current is 0? So if you have an open circuit condition, no currents can flow, then what voltage would you measure for a given temperature difference? Okay. So the way you can approach it kind of physically here is by saying that, okay, I've got no current flow, there's only one level, so the way you can have no current flow is if the Fermi function here happened to be exactly the same as the value of the Fermi function there. You see? Because what happens is, when you look in this contact, let's say this is the hot contact, and so the Fermi function sort of spreads out like this. Now, if you look at the cold contact, the Fermi function is not quite so spread out. And so, of course, ordinarily, this would be bigger than that and electrons would want to flow. But when electrons flow, what it will do is they will pile up here. Pile up because we are not letting them get out. It's open circuited. It's all open circuited. So, we're not letting them get out. Okay, so if you don't let them get out, then they'll pile up here, and because they pile up here, the overall electrochemical potential will rise somewhat. So it'll rise a little bit, like so. And so instead of being this red curve, it will now be this black curve. And the whole process will stop when, as a result, the Fermi function at that energy will match exactly what this one is at this energy. So basically the Fermi functions in the two contacts. So you see, we know that the Fermi function is given by 1 divided by e to the power, and we are interested in the value of the Fermi function at an energy equal to epsilon. So it is basically this. So for contact 1, the Fermi function is this quantity with mu1 and T1. For contact 2, it is same quantity but with mu2 and T2. And so, if those two have to be equal, then clearly what you must have is epsilon minus mu1 over T1 is equal to epsilon minus mu2 over T2. That's it. So, for a given temperature difference, this is the expression that tells you what is the correct potential difference. Because this will ensure that at energy epsilon, F1 exactly equals F2, and so no current flows. Okay. Now, here I'm going to use a little mathematical trick, and it's something like this. That if A divided by B is equal to C divided by D, then each one of these is equal to C minus A divided by D minus B. That's a little algebraic thing you can check out. Okay. So I'll use that here. So this is A, that's B. This is C, that's D. And so each one must be equal to C minus A. The epsilon cancels out. So what you get is mu1 minus mu2 divided by T2 minus T1. So you'll notice then, what we have here, though, that's basically the Seebeck coefficient. You see mu1 minus mu2, that's this open circuit voltage. I mean, times Q. There's a factor of Q, but other than that, this is it. And that's the temperature difference. So this basically tells you what is the open circuit voltage per unit temperature difference. And what is that equal to? Well, it's equal to epsilon minus mu1 over T1 or epsilon minus mu2 over T2. And if we are talking about small differences, then we can say that, well, all this is basically equal to epsilon minus mu divided by T. See? Because, you see, when you do a linear expansion, like what we did in the last lecture, you kind of assume that the mu's and t's are almost equal. And so, when we do write the transport coefficients this way, and you have a mu here and a t here, you don't ask whether it's mu1 and t1 or mu2 and t2, because the understanding is those would both give you almost the same answers. Okay? So what this tells you then immediately is that the basic Seebeck coefficient then would be epsilon minus mu over qt. The extra q is because, this is not quite the voltage, it's q times the voltage. So you'd have to divide by q. but that's it. So for a one-level device, you can see right away that the Seebeck coefficient is given by epsilon minus mu divided by qt. So if your electrochemical potential happens to be down here, and this is epsilon, so what you'd get, the Seebeck coefficient is determined by how far this level is from where your chemical potential happens to be, how far this is. You see? So the higher you put it, so if I had a level that was relatively high compared to the mu, then it would give me a lot higher Seebeck coefficient. And that is basically true. You see? If it is right on the chemical potential, is 0 Seebeck coefficient. If you go higher, you'll get a bigger number. If you go lower, you'll get a negative number. Okay? So that's true. Now, why then don't we look for materials whose density of states are way above the chemical potential? Well, the thing is, you do get a high S, but then that's not everything. You also want a good conductance. So what would happen is you would then have a device with a high S, but it would have a very low conductance, because after all, conduction, you see, is because of these electrons that are going through at this level. And if this level happens to be, say, 20 kT above mu, then there would be hardly any electrons going through. You'd kind of theoretically have a high Seebeck coefficient, but there would be this enormous resistance associated with it, which wouldn't be very useful. Okay. So that is why usually people try to put the level as high as possible without compromising the current too much, without compromising the conductance too much. And knowing that this extends out roughly over a few kT, you'd think that you could put this maybe at 2 kT above the chemical potential. So let's say this epsilon minus mu, let us say were 2 kT. It's in a good thermoelectric. You might, you're trying to put it as high as possible, but without losing the conductance totally. So you might put it at, say, a couple of kT up there. Well, in that case, the Seebeck coefficient would be 2K over Q. So generally speaking, a good scale of, what kind of Seebeck coefficient one can expect in real materials, this K over Q is a very good indicator of that. See, because that is roughly what you'd get in the best thermoelectrics, on that order. So how much is a K over Q? If you look at the numbers, K over Q. Now, usually, K is this Boltzmann constant, but what I normally remember offhand is KT at room temperature. So you could write it this way, and you see KT over Q is approximately 25 millivolts, and this is at room temperature, which is 300 Kelvin. You see? So that comes to about 1/12 millivolt per Kelvin. Okay? And I think you could write that as about 100. I think it's 90 or so, 86 maybe. So I'll just write approximately 100 microvolts per Kelvin. So that would be a good measure of what kind of Seebeck coefficients one can expect in a material. Now, here I did all this kind of in an intuitive way. Now, if you had actually gone through the expressions here, you would have got actually exactly the same answer. That is, you see, the expression I had was epsilon minus mu over qt. That's exactly what you could also get by just doing it formally, using the formal expressions. Right? And that's one of the homework problems. And we'll discuss it in the tutorial later. Now, let me tell you a little bit about the Peltier coefficient, for example. So the Peltier coefficient, again, is, what is it? Well, if there is no temperature difference, the question you're asking is, what is the ratio of the heat current to the actual current, to the regular charge current? And again, the idea is that every time an electron goes through this, and now we are talking of both sides at the same temperature here, like we discussed, like we just mentioned. So you got the same thing, same temperature both sides, but you're running a current through this. And the point is that every time an electron goes through, it carries an amount of charge Q, but it also transfers an amount of heat, which is epsilon minus mu, because it takes epsilon minus mu out of this contact and dumps it over there. So an electron carries an amount, every electron that goes through carries that much charge, and it carries that much heat. What that means is the Peltier coefficient, which is the ratio of how much heat is carried to how much charge is carried. So the Peltier coefficient must be epsilon minus mu over Q. And as we just discussed a minute back, Seebeck coefficient was epsilon minus mu over QT. And sure enough, the Peltier coefficient is temperature times the Seebeck coefficient, just like we talked about, the Kelvin relation. Okay. Now, what's interesting is also this last one, namely the heat coefficient. You see, that is the one which comes from calculating that quantity, GQ minus GPGS over G. Now, this is the one where, you see, formally again, if you calculated the heat current, again, that's part of this homework problem, you'll get 0. So what it tells you is that a single level device, a one level device, does not have any heat conductivity. So if no current is flowing, then for a temperature difference, there will be no heat current carried. Now that actually, if you think about it, almost looks obvious. If you think about this, because in a one level device, let me just clean this up a little bit since we messed this up somewhat. So you have this mu down here, and you have a one level device. So you have this one level here at epsilon. And the question is, we have put a temperature difference across this, no current flows, what is the heat current? And the answer is, of course, it's 0, because no current flows. Electrons are not going from left to right, and if electrons are not going from left to right, they can't carry any heat either. So you say, well, but is that true just of a one level device or of anything? Answer is no. That is strictly true only for a one level device. Why is that? Well, it's something like this. Supposing you had two levels. And you have a temperature difference. Now you see the total current, if you actually looked at it carefully, you'd find the total current is 0 since it's open circuited. I'm not letting current flow. But there is actually a current flowing at each of these levels. So there is some current flowing here, and there is some current flowing back here. So if you looked at it carefully, you'd find that at one energy, you'd have electrons flowing in one direction. At a different energy, you'd have electrons coming back. So that the overall thing is open circuited, so no net current. But there is actually kind of currents at different energies. But what that means is, you see, there's a heat current now. Why? Because let's say you got 1 electron per second going here and 1 electron per second going here. Okay, so overall, no net transfer of electrons, but then this electron that's going is carrying that much heat, epsilon minus mu, whereas the one that's coming back is only dumping that much heat from here. And so overall there is a net heat that's getting transferred. So once you have multiple levels, you see, you could always have heat current flow. I mean, you would have non-zero numbers for this quantity. So formally what you'd find is, if you're using these formal expressions, if you applied it to a one level device, as you'll see in the homework, this quantity will come out as 0. No heat conductivity. Whereas if you applied it to multiple levels, then you'd find that it will not be 0 because of this physical issue that I explained. And this is kind of important because you see, when you think about how do we make a good thermoelectric, and usually the answer is that when you look at a thermoelectric material, the usual, I guess, figure of merit is something like this. S squared G T divided by this heat conductivity. I'll write it as GK. Or instead of using G's, you could use conductivities rather than conductances. But it's the Seebeck coefficient squared times this normal conductance temperature divided by the heat conductance. And this is a dimensionless number. This is called the ZT product. This is widely used as a measure of how good a thermoelectric material is. And the way you can kind of see where this comes from is that if you had a material and you apply a temperature difference here, it will act like a little voltage source. You see, I earlier argued that this will look like a battery, a voltage source, whose magnitude is S times delta T, S being the Seebeck coefficient. On the other hand, it has a conductance which is G. And how much power can you extract from this? Well, it depends on what load you drive it with. But one of the standard results in electrical engineering, which if you don't know, it's not really part of this course, I won't go into it. But one of the standard results is that the amount of energy that you can actually extract from it, the power that you can extract from it, is given by this V square times G. And so the power you can extract is like S square G, times delta T square. So in a thermoelectric device, how much power you can extract depends on Seebeck coefficient square times the conductance. And this is often called the power factor. Now in terms of efficiency, the point is that you have to maintain this delta T across the device, of course, but then how easy it is to maintain a temperature difference kind of depends on this thermal conductivity GK. Because if it's thermally very conducting, then you cannot maintain this temperature difference quite so easily. And so a good figure of merit is the amount of power you can get out of it divided by the power that you have to continually provide in order to keep the temperature difference. And you can see this is kind of getting to this figure of merit that I had mentioned earlier, because you could write this as S squared GT over GK times delta T over T. So this would be like a material parameter that would tell you how good this particular material is. See, and this is widely used as the figure of merit. And one of the problems with thermoelectric materials is that this ZT product for a long time has been stuck somewhere around 1. And people have been trying all kinds of materials trying to improve it. And the understanding is if instead of 1, it could go up by a factor of 3 or 4, it would make a whole host of different applications possible, which are currently not economically viable things. But these could all become feasible if this number were bigger. And if you just looked at this, what we just discussed, you'd say that, well, the way to get good ZTs is find materials with levels that are sharp. Because we just argued that a single level device has no heat conductivity. So you say, okay, I got a 0 there, that should give me a huge number. Now that though is very far from reality, and the reason is that what we have discussed here is the heat carried by electrons. But in practice in solids, majority of the heat conduction is really due to phonons. And so what we just discussed here is GK due to electrons, and to this one has to also add the thermal conductivity due to phonons. And even if you made this 0, you're still stuck with the other one anyway. See?